So hello everyone. I think pretty much everybody is trickling in. So we're using a little bit the MIT rule of things starting at 05. But it's my pleasure and the pleasure of the whole community, right, to invite and listen to Pedram Hassanzadeh. So hello, Pedram. He's a professor at the University of Chicago and the director of the Climate Extreme Theory and Data Group. He just moved in from Rice University. He got his PhD and master's from the University of Berkeley. And he has received several awards, including the NSF Career Awards, the ONR Young Investigator Award, and an Early Career Fellowship from the National Academy's Gulf Research Program. So today is going to talk about the AI revolution and in weather climate modeling and the challenges with interpretability and predicting gray swan weather extremes. So it's our pleasure to have you present. If you have any questions during the presentation, don't hesitate to ask. Like we try to do these meetings a bit more lively than all of us disappearing and coming back at the end. If you can also put questions in chat, and then I will try to monitor that, as well as Julie and Gerardo and Moss. But thank you very much again, and the floor is yours, Pedram, and thanks again for accepting the invitation.
Great, thank you very much for the invitation, and I'm very excited to be here and tell you about some of the work we have been doing in the past few years and using tools from applied math and physics to address some of the challenges that AI models, particularly deep neural nets, have in addressing, in improving climate and weather prediction. And today I'm going to talk about two of these challenges. One is interpretability, and the other one is predicting gray swan weather extreme events. And I'll tell you more about gray swans, but basically these are events that are physically possible, but we don't have them because they're rare. We haven't seen them in the observational record, in the context of AI, in the training set. But these are events that are actually the strongest ones, and we are actually most interested in predicting them, whether for early warning or understanding the changes with climate change. So I'm going to focus on these two. But because it's a broad audience, I'm going to start with some introduction and talk about climate research. So climate research is increasingly becoming more important, but it's a complicated area because it involves understanding complex interactions among highly complex systems involving the Earth system and the human society. For example, in climate research, we have to first understand how the Earth system would respond to the increase in greenhouse gases, for example, how the global temperature will increase. And then more importantly, we have to understand how extreme events like hurricanes or heat waves might change because of the increasing greenhouse gases. And then you have to understand the socioeconomic and environmental impacts of these changes, and then formulate mitigation and adaptation strategies. So in the past few decades, in different disciplines, tools have been developed for each of these steps. But the problem is that each of these tools the predictions come with a high degree of uncertainty. And the worst is when we put all of them together, we often get very high uncertainties about what could be the potential impacts of climate change and what kind of solutions we have to basically formulate. So often we see these kind of headlines in the news about potential mitigation adaptation strategies. So now in the past few years, there has been a lot of interest in how AI might help with reducing some of these uncertainties. And so my background is in fluid dynamics and computational applied math and climate science. So I will mainly talk about using AI to reduce uncertainties in this top row. It's about climate physics. But as you can imagine, there's also a lot that has to be done in this bottom row, which involves also climate-human interaction. So the main tools that we have for predicting climate physics are basically numerical weather and climate models, which are basically a result of a revolution that happened around in like over 50 years from 1950 to 2000. This is where we figured out basically how to numerically solve the differential equations that govern conservation of mass and momentum and energy in the atmosphere, in the ocean, and in the whole climate system. It has been a major scientific achievement. To tell you a little bit more about its history, this is a field that actually started by the success that John von Neumann had with using the first digital computer, the ENIAC, to do the first successful weather forecasting, and that really started this field of numerical weather and climate prediction. But the history actually goes back a bit more, and it really started by Richardson's first try in doing numerical weather prediction, which was the idea of let's get these Navier-Stokes equations, initialize them with the observations we had, and integrate it in time, which is most people back then thought this idea would not work, and they tried it once, and it failed so badly they never tried it again. And in fact, it took around 20 years for Courant and others who were developing numerical, who were doing rigorous methods for numerical analysis to figure out what the problem was, which was the CFL condition. And it took another 20 years for von Neumann to get the first digital computer to do this successful forecasting. The message here is that really weather and climate prediction really required close collaborations between people in different fields, climate, numerical analysis, applied math, to closely work together and make these happen. Also, I want to say that in this gap of 40 years, atmospheric science really had two sides in terms of how to do any kind of weather prediction. One side was led by people like Rossby, who was actually the chair of the meteorology department at U Chicago, and he really wanted to use the first principles and physics and PDEs, except that he just couldn't solve the equations. And the other side was led by Eric Craig, who was the chair of meteorology department at Caltech. And he was really a data scientist. He wanted to do weather prediction with pattern matching. And he had some success. For example, for the Normandy landing, they actually used that approach. But after the success of von Neumann's work, basically everybody moved in the direction of doing numerical weather and then climate prediction. Still, Ed Lorenz actually revisited this idea of doing weather prediction just from data. And he wrote this paper, which he basically argued that to successfully do weather prediction, even for like 5 days by learning from the past data, we really need a very, very long data set. And there is a paper from 90s that actually put a number on this analysis that Lorenz did and argued that we need 10 to 30 years of observational data to be able to do successful forecasting for 5 days. But as I'll show you soon, actually with deep neural net, we now have done this very successfully with just 40 years of data. So I just want to tell you a little bit about the history of this. So now the numerical weather and climate modeling has been very successful, but as the models have become more accurate, they also have become much more complicated and much slower. And this is because basically the climate system is multi-scale and multi-physics. This cartoon just shows the range of time scale and length scales that we have in the atmosphere alone, from seconds to thousands of years, from millimeters to tens of thousands of kilometers. So to resolve these scales, the climate models have they need higher and higher resolutions. But as you can imagine, that would basically cost the computational cost of these models. The schematic here just shows like how the resolution of the climate models has improved over the past few decades. We see that currently the typical resolution is 100 kilometers, but this is very far from the resolution of what we call the digital twin, at least in the atmosphere, which is a resolution of 1 kilometer. As you can imagine, to get that resolution, we are far from getting there. So let's go back to the problem of uncertainties. And let me tell you where these uncertainties in weather and climate prediction come from. And as Pierre mentioned, again, if you have any question, please ask. Otherwise, I'll just keep going. So there are 3 major sources of uncertainty when we think about climate prediction, and 2 of them are also relevant to weather forecasting. And now we have tools that we can actually quantify the contribution of these uncertainties to predictions. For example, if you are interested in doing in projecting how the global mean temperature would increase as we increase CO2 over years, we can see that, for example, the epistemic uncertainty, the model error in year 2040 would contribute 50% of the uncertainty. Another 40% would come from what's called scenario uncertainty, which is we are not sure how much CO2 we are going to put into the atmosphere and how much of it we might remove with things like geoengineering. And then there is a little uncertainty that comes from the fact that we are dealing with a chaotic system. So there is basically sampling error. And you can see that basically these are also the 3 common sources of error in a lot of other problems in science and engineering. For example, in engineering, the scenario uncertainty would be basically the design space that you have to explore. Now here it might seem that actually most of the error comes from scenario uncertainty, but as we go to actually more extreme events, smaller scales, we actually see that all three sources of uncertainty are important. For example, if we look at precipitation over East Asia, now we see that model uncertainty remains like the major source of the error. Internal variability becomes important. And again, as we look at the smaller scales, extreme events, all three would become very important. Now, the challenge is that reducing these three sources of uncertainty sort of need different type of models. So reducing the epistemic error basically needs more accurate models, which often requires higher resolution, so models that become more expensive. On the other hand, reducing scenario uncertainty and internal variability uncertainty requires models that are fast, so we can do very long simulations or do multiple simulations, explore different scenarios. So basically, the challenge is that if you want more accurate models, they will become more expensive, but then it would become hard to reduce these two other sources of uncertainty. So in the past 7-8 years, with the basically AI revolution happening in many areas, including science, many people have started asking the question, well, can we use AI to reduce these uncertainties? And so different ideas have emerged. Of course, one idea is let's use AI to develop just more accurate models. And maybe we can use AI to develop a better understanding of climate physics. But also, more importantly, maybe we can use AI to develop better parameterizations, better closure models, approaches for multi-scale modeling. Another idea that has emerged more recently is that maybe we can develop fast AI climate emulators. You can think of them as surrogate models, that basically these are very fast models and they can help with reducing these two other sources of uncertainty. So I'm not going to spend a lot of time about parameterization. Many of you are probably familiar with the general concept of closure modeling, multi-scale modeling, parameterization. I'll have an example about 2D turbulence that I'll talk about it later. But I want to mention that recently we wrote 2 review papers for the general physics and applied math community. And we went through a lot of these ideas about using AI for these 3 sources of uncertainty. So you can check them out. But in the talk today, I will talk a little bit about parameterization and a little bit about these AI climate emulators. Now, the idea of these climate emulators, it's really built on the really remarkable success that AI has have had in weather forecasting. So the idea here is rather than using Navier-Stokes equation, conservation laws to do weather forecasting, we can train a big neural net to take the current state of the global atmosphere, this state vector U, which has temperature, velocity, pressure, humidity, and then predict it a few hours later. And then we can put this back and basically march in time, basically as initial value solver. And we can basically find theta, which are collectively all the weights and biases of these neural nets, by minimizing like an MSE loss. This idea emerged in like around 2016, 17, and some groups, including my group, started working on it. Most people believe that this is not going to work until this paper showed up, which introduced this model called ForecastNet. This was developed by NVIDIA with my groups and a number of other groups contributing to this. And here we showed that actually by this approach, you can get close to the accuracy of the best numerical weather models that we have, while the models we develop are actually 100,000 times cheaper and faster during inference than the numerical models. There's a bit more information here about exactly what we trained on. And here is just a movie of water vapor out of sample prediction. This is from prediction from the model. This is ERA 5, the data it was trained on. And you see that, for example, if you're interested in atmospheric rivers over Western US, up to like 4 or 5 days, the model actually does a pretty good job. You kind of notice that some details over the tropics are missing like a small scale features, but overall, the accuracy in many metrics are actually as good as the best numerical models. And very soon, a number of other tech companies jumped in and developed deeper models, did more ML engineering on basically optimizing the models, and developed models like Pango and GraphCast that then can robustly beat the best numerical models like the European model called IFS in terms of global weather forecasting, but also forecasting of extreme events. Particularly, they have been very successful in forecasting the track of hurricanes. At this point, the European Weather Center, which is the leading center in doing weather forecasting, agrees that these AI models are basically better than the physics-based models. So they have developed their own AI model. It's called AIFS. This is a plot from their website. You see that basically by using AI, you'd get like half a day improvement in the weather forecast. But again, the revolution is not this half a day increase in the lead time, but it's really the fact that these models are much, much faster, which, as you can imagine, enable us to reduce the uncertainty, to improve data assimilation, and they have many other advantages. So now this is about weather forecasting, but there are ideas of how to actually use this to also do climate prediction. And I'll be happy to talk about those in Q&A. So there has been remarkable success, and there also has been success in doing parameterization with AI, but also to really use these approaches operationally and in practice and reliably, there are a number of major questions and challenges, and this is what I mainly want to talk about. So a lot of these challenges are common in use of AI in any problem in science and engineering. Probably many of you are currently working on addressing these problems in your specific field, but basically, some of these challenges are what's that you actually need to learn. In a lot of problems, actually, it's not so trivial. It tells us actually what should be the right loss function and metric. We often have to do this kind of training in the small data regime, which can be a problem. We know a lot about the physics of our systems. So the question is what physics to include and how to include it. There are major challenges about learning rare events, causality, and how to do UQ. And then there are other challenges, interpretability, how to do out-of-distribution generalization, especially when we are thinking about climate change. We are dealing with a non-stationary system. And then people are more and more noticing that many times the AI models can actually lead to instabilities or producing unphysical results, including some of these weather models start producing unphysical results after a few weeks. So in today's talk, I'm mainly going to talk about one example from rare event, dealing with rare events, and one about interpretability. So in my group, in the past few years, we have been developing a hierarchy of systems that we use to look at some of these problems in using AI for turbulence modeling and especially for AI for climate and weather prediction. And we try to basically identify questions and challenges when these methods are used on real world systems, go to much simpler systems as simple as Lorentz, try to understand what's going on, maybe develop better methods, and then go back and make sure that the approaches are scalable. So the first example I'm going to talk about is about some work we did on developing parameterization subgrid scale models for two-dimensional turbulence as a basically prototype for geophysical turbulence, for turbulence in the atmosphere and ocean. Many of you are probably familiar with this test case, but basically it's governed by the Navier-Stokes equation. Here, I'm just showing you the equation in the vorticity and stream function. This is the Reynolds number, and the system has some forcing and damping. And we can solve these equations. We can do direct numerical simulation with high enough spatiotemporal resolution. In this work, we treat that as the truth. But doing DNS in something like the atmosphere or ocean is impractical. So what people really do is largely simulation, which, as the name suggests, basically means that we only resolve the large eddies and we try to parameterize the smaller scales. So we can derive the equations for LES. Basically, we can low pass filter these equations. And we know that once we do that, we can write these equations almost explicitly in terms of the filtered variables, except that at the end, we will end up with this term that's called the subgrid scale term. Because of this quadratic nonlinearity, we cannot write this explicitly in terms of the result scales. Sometimes you see this term written in terms of those time terms. This is where the smallest scales are. So computationally, the advantage of solving the second equation, the LES equations, is that we need much lower spatiotemporal resolution. But the challenge is that we need a model for a closure model for the subgrid scale term that I'm going to call pi. And for decades, people have worked on developing closure models based on physics. For example, we have Smogorensky type models, eddy viscosity models, which assume that this pi term is mainly diffusive. So we get a term, we can represent it like this. The problem is that when we do this, the models become too diffusive and often we don't capture the extreme events. We can see that even in this simple system. For example, here I'm showing you the PDF of vorticity, which is really the weather in this system. The black line shows the PDF from the truth. We see that the Smogorensky model and a more advanced version of it, they basically can't capture the tail of the PDF. They can't capture the extreme events because they're diffusive. So the question is, can AI do better? Can we, for example, use a neural net to find this mapping between the subgrid scale term and the result scale? And you might notice that there are actually results with the CNN here, the blue line, which actually does that really well. But we actually had it to address a number of problems about instability and the amount of data we needed to address that. Before telling you a bit more about that, let me introduce the neural net that we use in this work. So we trained a CNN to take these snapshots of the result flow and predict these subgrid scale term. It had 10 layers. I'm going to go through some of the math because I will need to use it later when I talk about the interpretability. So this is basically the governing equation of a CNN. So here, this G, this is the activation. This is the output of a layer and a channel. Here, its size is 128 squared, which was the size of the LES grid. And the activation from one layer depends on the activations from the previous layer after these small matrices, these are the convolution kernels, do convolution on them, which is the operation that's shown here. And we also have a small number of biases. Everything is linear here. At the end, there is a nonlinearity. When we train a CNN, basically these kernels, which are here 5 by 5 matrices, these are the main things we learn. So here we have 10 layers. We have 64 channels. Each channel has 64 kernels, and kernels are 5 by 5. So overall, we have 1 million learnable parameter here. And we can learn these weights and biases, theta, basically by minimizing the loss function. So as much as deep neural nets are called black boxes, the equations are actually not that complicated. Of course, the challenge is it's hard to know what they have learned and why. For example, here, this is one example of those 40,000 kernels that we have. And it's just hard to look at these and see anything meaningful here. But in a few minutes, I'll tell you how we can do a Fourier transform of these equations and actually understand what these kernels are doing. And so here the idea is that once we train the CNN, we can then couple it to the LES equations, and now we can integrate this in time. Okay. So we basically follow this approach, and first we found out that, well, we actually need a lot of data for these to work successfully. And in this paper that was published in JCP, we actually used the understanding that we have of the physics of 2D turbulence to actually explain why you need a lot of data. I'm not going to go through those details because of time, but if you're interested, I can tell you more. But once we understood why we need a lot of data, which has something to do with backscattering, which is basically like anti-diffusion, in another paper, we showed that we can actually now add physics and get the approach to work with a much smaller amount of data. So we got a CNN that could do subgrid scale modeling really well, better than any of the other physics-based models. It was data hungry, but by adding physics, we could show that you can make it data efficient. But still, we really wanted to understand how this model works. So we started thinking that, well, when we study dynamical systems, turbulence, very often we look at our equations and data in the spectral space, in like the Fourier space, because that's where the physics, the equations might simplify. So we thought to do the same thing with the neural network. So rather than trying to use the interpretability methods that are developed in ML and bring them into our field, we thought to actually use what we have always used to understand the physical systems and apply it to these deep neural net. So to remind you, this is the governing equation of a CNN. Everything in blue is just linear. I'm going to call that H. Remember, there is a convolution operation here. I can use the convolution theorem and basically write the Fourier transform of this H, which basically tells me that we need a element-wise multiplication between the Fourier transform of those kernels and the Fourier transform of the activation. Even though there is a nonlinearity here, which in this case was rel U, we can actually analytically write down the Fourier transform of this G, which you get this sum, which basically comes the Fourier transform of the Heaviside function. But this basically tells us that what controls the spectrum from layer to layer and eventually from the input to the output depends on this sum, but most importantly, it depends on the Fourier transform of the kernels, which suggests that instead of looking at our kernels as these 5 by 5 matrices, we should actually look at them in the Fourier space. Now, remember that these 5 by 5 matrices do convolution on these 128 squared matrices. So to get this Fourier transform, we basically pad it to 0 to 128 squared and do 2 DFFT. And this is what we get. So here, this X is the wave number in the X direction, wave number in the Y direction. And we see that basically this kernel is some sort of filter that's zero everywhere except at the center. So it's basically a low pass filter. So we did this for all these 40,000 kernels that we had in this work. And we saw that in the Fourier space, a lot of them are actually very similar. So we just came and clustered them. Here I'm showing you the cluster centers of the 4,000 kernels in layer 2 and layer 10 of 3 CNNs trained to do subgrid scale modeling at 3 different turbulent flows. And we see that there are actually a lot of similarities between what these CNNs have learned. They have learned a lot of low-pass filters, a lot of high-pass filters, and they have learned these interesting band-pass filters. And a little bit more work showed that these filters are actually Gabor filters. So if you take a sine function, multiply it with the Gaussian, you actually get these kind of wavelets. And if you do Fourier transform of these, you get this. So basically what these do, this filter, they basically pick up the wave numbers that they see, but at basically a specific band. So this is exciting because now I can tell you that the million learnable parameter that we had in this CNN, they actually turned into just a few classes of low pass, high pass, and Gabor filters. Now, I should say that in the machine learning community has been known for over a decade that CNN, especially for classification problems, they actually learn low pass and Gabor filters. There have been very nice papers by Stefan Mallat and others showing that. But even beyond that, in sparse coding and in neuroscience, there have been papers that show that if you try to learn multi-scale localized oriented features, which are the kind of features we have in turbulent flows and in atmosphere and ocean, we basically, these are sort of the best basis functions to use. And the key to learn these are actually the sparse learning. And this is like a very nice paper that from neuroscience that explains some of these. So this is exciting because it says that we can actually now understand what this CNN was learning. And so it suggests that, well, maybe by doing more work, given that there's so much redundancy in the kind of wave numbers that we are learning and similarity between hundreds of these kernels, maybe we can start developing some reduced order models for some of these CNNs, at least for the purpose of analyzing them and understanding what they do. Probably we can develop some sort of skeleton models if we look at the CNN in the Fourier space. Now, this is still not easy because we have layers and there's no linearity between them, but there's a lot of interesting work going on in the machine learning community and the theoretical side, trying to develop this kind of end-to-end analysis of neural networks in the Fourier space, which we can bring in to our field. So I think there's a lot of potential here. This is not just limited to CNNs, for transformers, for a lot of other networks. Doing this kind of analysis in the Fourier space, especially after activations, we have found it to be very useful. Now, understanding what's going on end-to-end, it still needs some work. But when we do transfer learning, which is something we found essential so that these neural nets can extrapolate in parameter space, for example, we have shown that you can get these neural nets to do successful parameterization for like 100 times of the Reynolds number, with transfer learning, we can use this kind of approach to understand at least what's learned during transfer learning. Because of time, I'm not going to go through the details, but we have a couple of papers and a few more in the work that we show that when we do transfer learning for turbulence, and now we have been looking at some problems directly related to climate prediction, this approach of looking at everything in the Fourier space tells us a lot about what the neural network is learning during transfer learning, and we can actually connect that to the physics. So I just wanted to introduce this approach as a way of really bringing ideas from applied math, from machine learning theory, and from climate and turbulence physics together to develop frameworks for interpretability. And in those papers, we actually dig more into some ideas from machine learning, like looking at the loss landscapes and things like that to really explain basically how to interpret these Fourier analysis. So this is one thing I wanted to mention about interpretability, which I'm very excited about. And I think some of these ideas can be combined with other ideas that have been developed in the machine learning community for interpretability to improve how we can explain and interpret what neural networks are learning when they apply to these kind of problems in turbulence modeling or weather and climate prediction. So the second problem I want to talk about is around rare events that are so rare that we even haven't seen them in the training set. So in climate science, in the past few years, at least since this paper from Lin and Emmanuel in 2015, people sometimes call these events gray swans, which basically you can define them as extreme events that are physically possible, even for a stationary climate, but we just haven't seen them in our observational records. So you can basically think of them as, at least in the concept of AI for climate, events that are physically possible, but we haven't seen them in our training set. For example, currently, a lot of weather forecast models are trained on 40 years of high quality observational data that we have called reanalysis. But then you can imagine that there might be events that have a return period of 1,000 years. So if we had longer observations, we could have seen them, but we just don't see them in these events. But these are really the events that we want to make sure we can forecast for early warning. And these are the events that when we develop climate emulators, we want the climate emulators to enable us to sample them. I want to say that gray swans are different from black swans, who are events that we really don't expect any model, even physics-based model, to predict them. Like, for example, if you have a volcanic event or something like Chicxulub impact, that really it's a one-in-a-lifetime event and a black swan. But gray swans, we really need to be able to predict them. So we wanted to see if these AI models can actually forecast these kind of events. So one event we looked at was this extreme rainfall last April in Dubai that, if you remember, resulted in a lot of flooding in Dubai and in UAE in general. If we look at the PDF of precipitation around Dubai, this is where this event was. This is what we have in our training set, which is from 1979 to 2015. So we see that this was twice more rain than anything this model has seen in that region. So we really didn't expect the AI models to be able to forecast them. So we forecast the AI models like 5 days before the event. These are all global initial conditions, but here I'm just zooming in into Middle East. So this is the initial condition on April 11th. This is what happened on 16th. So we wanted to see if, starting here, some of the AI models can predict this event. Now, surprisingly, the few AI models that actually can forecast rain, they did very well. This is the forecast. This is forecast from GraphCast on 16th. This is from the model called Fushi. And you see that they actually get the circulation pretty well. These arrows are the wind vectors. The lines are basically pressure maps, and the shading is precipitation. And you see that they actually got the right location and almost the right amplitude. If we basically do some averaging and make a time series, we see that this is the black line is the observed rainfall. The blue line is the 5-day forecast from GraphCast, which actually did very well. Notice that there is a dashed line here. This is the most amount of rain that this model had ever seen around Dubai, which is here. And you see that the model actually comfortably goes above that limit and does a good forecast, also gets the decay right. Fushi doesn't get the amplitude quite right, and I can tell you why that happens. But we see that actually the AI models do much better than what we expected in capturing this gray swan event. One thing just about the advantage of the model in terms of computing, the numerical models, the IFS, also did very well in capturing this event, but it basically requires around 13,000 CPUs for 1 hour on a supercomputer. But then these forecasts were generated for 90 seconds on one AI100 GPU, which, as you can imagine, have a lot of advantage in when doing this kind of state-of-the-art forecasting becomes so cheap and accessible. Okay, so we wanted to...
Maybe one question, maybe, Pedram, this peers.
Sure.
So the Fuxi and GraphCast, they were initialized from Era 5 reanalysis or in these predictions?
Yes, they were initialized with, so they're all trained on Era 5, and they were initialized 5 days earlier on Era 5.
Got it. So like if you wanted to do that, and maybe there's more questions for the future, but like in practice, you would want to get rid of era 5, right? If you want to replace it.
Yes, absolutely. So in practice, so era 5 is released like a few days of delay. Then, of course, you lose a few days just because of that. Now, NCEP, the US reanalysis, actually released after just 6 hours. And I think NVIDIA showed that even initializing from NCEP, you can actually do very good forecasts. So in terms of, practically, that's not a problem. But I think maybe what you are alluding to is even training these models more directly on observations, right? And ECMWF actually has a paper that they show that that approach itself can be very promising. But yes, down the line, we really want to have the data assimilation component all integrated. So, and also one thing to mention is that precipitation in era 5 itself is really not that great. It doesn't quite agree with observations. If you look at the news, the precipitation was around 200 millimeter, which in era 5, you sort of average out, get 60. So certainly that's where the community is going in actually using more direct observations for this kind of forecasts.
Okay, thank you. Yeah, I think Julie also has a question.
Yes, thanks. I have a quick question also. So you're training on era 5, like how how far or what type of temporal window are you using to train on era 5 actually specifically for that event?
So the models are already trained. So we are not training it for any specific event. So all these models are trained from 1979 to 2015.
Okay.
And then they use 2016 to 18 for validation. So we do all of our testings from 2018 and onward.
Okay. Yeah. Thanks.
Sure. Okay. So we wanted to understand how come this model can actually predict this gray swan, which is, much stronger than anything this model had seen before. Now, I should say that models like GraphCast and Fushi are actually very expensive to train, but ForecastNet is actually a model that is moderately cheap. So at the university with limited GPU computing, we can actually train this model from scratch. So we had actually started doing some work on ForecastNet and asking a similar question about gray swans, but for tropical cyclones. So what we have done here is that we have trained several versions of the model when we remove category 3 to 5 hurricanes from the training set. So this schematic sort of shows what we did. So we trained a model we call ForecastNet full. We trained it 5 times just from random initializations, and we used all the data from 79 to 2015. We also trained another version that we call NoTC when we removed any day when there was a category 3 to 5 hurricane anywhere in the world. And we basically lose 25% of the data. And then we trained another version we called random when we randomly remove 25% of the data. So we wanted to see whether these models can actually predict category 5 hurricanes from the testing set. Now, notice that category 5 hurricanes are gray swans for this NoTC because they have never seen anything beyond category 2. Now, many people think this should not work because, of course, rare events cause data imbalance, and gray swans are really the symptotic limit of data imbalance. We even haven't seen anything like them. And generally, we shouldn't expect the AI models to do out-of-distribution generalization. On the other hand, some people think this should work because it seems that these models are doing more than just memorizing patterns. They do some degree of learning. And there are a couple of nice papers that they have done some interesting experiments showing that these models are not just memorizing the patterns. So when we started these experiments, the idea was, it is possible that these models can learn from weaker events like category 1 and 2 that they have seen in the training set, and they can still do some degree of extrapolation to category 5. So that was the purpose of these experiments. So we did this. We're now testing these models on category 5 hurricanes. This is for Hurricane Lee. So this is the black line here. This shows the evolution of sea level pressure at the center of this hurricane. The dashed line here, that was the limit below which NoTC hasn't seen any kind of sea level pressure. So as the sea level pressure goes down, the hurricanes become stronger. So this is the limit of category 5. And we see that ForecastNet full actually can do a good job in predicting a category 5 hurricane that went through rapid intensification. The random model, which had 25% less data, actually does very well too. But this is what the NoTC did. You actually see that this model predicts a weakening of a hurricane and sort of saturates around the limit that it had seen before. So it basically tells you that you are going to get a category 2 hurricane while it's supposed to get a category 5 hurricane. So what we see that, no, the model actually cannot predict gray swans. And the problem is that it actually gives you false negative. It tells you consistently that you are going to get weaker events. I showed you one example here. I'm showing you results aggregated over 20 category 5 hurricanes in the test set. Again, ForecastNet full. The first row, this is where we initialized the hurricane when it was weak. Here we initialized it when it had already reached a strong phase of hurricane. We see that full and random, they can do very good forecasts, but again, no TC, it cannot predict the event well. So we basically see that these models cannot do this kind of extrapolation that some people think they could do. So then we start asking the question, well, how come for the Dubai event it worked? It was there were different kind of models. For the Dubai for GraphCast and Fushi, we cannot do these experiments. It become extremely expensive. So in ForecastNet, we did two other experiments. So we only removed hurricanes category 3 to 5 only from the Atlantic Ocean or only from the Pacific Ocean. And then we see that the model that had only seen hurricanes over the Atlantic, it can still actually do a good amount of forecasting over the Pacific and vice versa. So we basically suggest that these models can learn from dynamically similar events in other regions and use that information in another region. So because of time, I'm not going to go through the details, but we actually put up this paper on arXiv if you're interested in seeing all the results. But basically what we see is that these models cannot predict global gray swans. If there are events that would happen that these models haven't seen anything like them anywhere in the world, these models are not going to be able to capture them. And given that basically all the current models, even the models that are called foundation weather and climate models, use very similar learning process, we expect this problem to also happen for them as well. However, what's encouraging is that these models can actually learn from dynamical similar event in other region and use that knowledge in a different region, which can be very promising. I should say that for the Dubai event, we have shown that actually events much stronger than what we saw in Dubai, they had happened over other regions in the world when they get more rain. Very similar dynamics, just stronger events. So it seems that the models have learned from those. So now, for these AI models to be really useful for forecasting, and also when we turn them into emulators that will be trained on short data sets, and they're supposed to generate long synthetic data sets and let us reduce the sampling error for extreme events, we really need to be able to deal with gray swans. So the question is, how can we fix this problem? And we think we really need innovations at the intersection of AI, physics, and math. So of course, the first idea that comes to mind is to add physics. But it's not clear to us what is the physics that need to be added to fix this problem and exactly how to add that physics, but that's something to explore. In machine learning, a common approach to addressing data imbalance is by basically weighting the loss function. You can weight your loss function to inflate the importance of rare events during the training. That would probably improve the learning of the real events that the model has seen, but I don't think that would help with gray swans. This is something we are testing. Oversampling is another idea that's used in ML to deal with rare events. But here the problem is, where do we get gray swans? Some people think about using generative models to train it on some data set, then sample and generate more extreme events. I don't think that idea would work. There are papers that already show that if you iteratively use generative models to train them on their own output, they actually collapse. So I don't think that idea would necessarily work. One idea that I think can be promising is to use physics-based models and try to actually generate more strong TCs and then add them to the training set. But the idea that we are really hopeful that would work, and this is the main idea that we are pursuing in our group, is to actually combine ideas from rare event sampling in applied math combined with active learning and combine those with these AI models. So rare event sampling is an idea that has been around for a while to deal with extreme events. For example, one idea in rare event sampling that's already been shown to be very promising in weather climate applications. There are papers, for example, like the one I'm citing here from Dorian Abbott at Chicago and Jonathan Ware at Quran, is that we can generate an ensemble. This can be from a numerical model And then we can identify which of the ensembles are going toward like an extreme event. So we can terminate the other simulations and then branch out from the one that is actually going toward extreme events. And again, we can continue doing this and sort of, for example, if this y-axis becomes like temperature extreme, we can actually try to nudge the ensembles who are generating more extreme events. And this approach actually has been very interesting. For example, there is this nice paper from Freddy Boucher's group that they use this approach with a cheap GCM numerical model. And they show that if you basically do 1,000 years of numerical simulation, you can predict the return period of events that have a return period. You can basically deal with events that have return period of like tens of thousands of years. Still, this is expensive to do with a state-of-the-art numerical models. So one idea is to actually use an AI emulator, which especially in short term, they can have very good forecast skill to sort of guide a physics-based model where to sample, where to generate new physics-based samples, and then add those samples to the training set of the AI model and sort of iteratively, basically like active learning, try to generate more physics-based samples and add them to the training set of the AI model. So this is an idea that we are currently pursuing in our group. So this was the second example that I think, again, how combining ideas from machine learning, math, and physics can help us with dealing with rare events for this kind of weather and climate prediction. So I think this is a good place for me to stop. And I'm looking forward to more discussions and your questions.
Thank you very much, Pedram. Thanks a lot for the great presentation. We can clap a little bit. So anybody has any questions? So Julie, I think, has one question.
I have one, but I can also let other folks ask. So, you know, you were talking about the prediction of those the heavy precipitation in Dubai and then also the tropical cyclone, and so you draw this conclusion that global versus regional may give you predictability or not, right? Don't you think also, I mean, is there a difference depending on which variable you're trying to predict also? Because in Dubai, you're trying to predict the precip, whereas the tropical cyclone, at least for what you're showing, you are interested in the sea level pressure. So have you seen also transferability or not that gives you predictability depending on which variable you're targeting, right? Because those two events were really different.
Yeah, that's a great question. So I should say
variable in the state.
Yeah, so these models, of course, they predict the whole state vector, right? I'm showing you like precipitation and sea level pressure because these are the common metrics of looking at like a, rainfall event or a tropical cyclone. But of course, for the model to do good forecasting on one, they sort of need to get other things right as well. Like, for example, you're looking at the circulation and things as well. But I think generally, and this is something that we actually discussed it in that paper on the archive, that, I mean, we have to develop a better understanding of how to analyze not just one variable, but the whole state vector. Because one thing that I'm not showing here because of time is that even when we remove basically low pressures from the tropics, we didn't remove them from extratropics. So actually, pressure level at the level of Category 5 hurricane still exists in the extratropics because of extratropical cyclones. However, the model actually didn't learn from them because, of course, tropical cyclones and extratropical cyclones, they just have different dynamics. Now, the AI model doesn't know anything about dynamics, but it sees a different state vector. So I'm trying to see whether I have that in my backup slides. Maybe that would just take more time if I try to find it. But so it seems that even like what is a gray swan, actually, we have to think about it more because sort of we have to understand the whole state vector, at least the key variables that would be in the model. So again, the no-TC experiments had seen low pressure at the level of Category 5, but they hadn't seen the right relationship between the input and the output. So yes, I think this is just something to think about more because we shouldn't just think about one variable and whether that is out of distribution or not.
Okay, thanks. Thanks.
Thank you. So Martin, you can go next if you would like.
Thanks. Yeah, I mean, one of the themes in machine learning seems to be sort of being able to understand what you don't know. So what hope is there in this setting of trying to understand what you don't know in terms of, the models? I mean, you can see that the models don't work in certain situations, but, what's the general methodology for sort of moving forward in that direction in the future in terms of understanding what you don't know from one of these models?
Yeah, I think that's a great question. I think maybe there are two ways to think about what we don't know. I think sometimes we just want to develop a better understanding of the physics. For example, for parameterization, I like to know how to develop a closure model, right? I mean, this is a question that has been around for a long time, and whether there is a way to better understand like this CNN that works so well and develop a fundamental understanding of how to develop a closure model. But I think the other question is, if I can do better prediction, if I can do a better emulation with the AI model, if you tell me how hurricanes over Florida might change with climate change, I think that's also would tell us something about something we don't know. But there's a question of to what degree I can trust that new knowledge. So I think there is just some degree of understanding that comes from a better forecast or emulation, and there is a understanding that can come from development of fundamental knowledge. So for the first one, like if a weather model, if one of these models can tell us how some extreme events might change in the future, I think developing good models for uncertainty quantification, I think that would be essential so that the AI model to some degree can tell us when we shouldn't trust that model. And there are common methods in machine learning for UQ. To what degree they can actually be useful for these kind of problems, I think that's still something to be seen. But also, I think just looking more into what these models can do and cannot do, I think that could be something very useful. These models, like the AI weather models, they are doing things that are very surprising. We didn't expect them to be able to do. And there are things that actually cannot get right, and everybody thought they should be able to get right. So I think we are at that stage that there are a lot of interesting papers coming out, pointing out some of these things. So I think like looking more into these models can be very helpful. I don't know if I answered your question, but
that's a great answer and a great talk. Thank you very much. I didn't expect that. You gave me exactly what I kind of thought the situation was. Thank you.
Thank you.
Thank you again. So I think Antonio, you can be next, and then VJ in the chat.
Yeah, first of all, thank you very much for a very nice talk. My question is very simple. Of course, the issue of out of sample, let's say, predictions is central to the discussion right now. But I had the impression from your discussion that this is not a general statement. It's really depending on what kind of event you're trying to, focus your attention on. So we are still not sure that the ML AI model are not really capable of doing out of sample prediction. But so I just want to have your reaction on that.
Yeah, I agree. And in that paper, we try to be careful to what degree we can generalize these findings. We only did this for tropical cyclones. Now, whether this would work for heat waves or not, these are experiments we are doing. It just becomes very expensive when you have to train these models from scratch many times. It just needs a lot of GPU power. And in that paper, we discussed that, I mean, for things like heat waves, when the essential components are basically zonal and meridional advection of temperature, of heat, and maybe some basically adiabatic warming, I mean, it is possible because those are very common phenomena, and the model would see them in many places. It is possible that for things like heat waves and cold snaps, the models might do better than what we see here for tropical cyclones. But I think we just need to do those experiments and see to what degree this would apply to other extreme events. I think it has a lot to do with the physics of the process and the state vector, which becomes a little high dimensional. So it's hard to, just easily understand how to make sense of the different state vectors for these different events.
No, I agree. That of course depends on the physics. That's another place where the physics is coming in. But it would be interesting to find a way to predict which event will be more probably described and which are not. Okay, anyway, thank you very much. Yeah.
Absolutely. I think developing benchmarks for these models would be essential. I think we need to, because the AI models, when they're trained for most of the observational record, they only leave us very few years for basically out of sample testing. And when we are now looking at things like seasonal forecasting, like monsoon onset, when you basically get one sample per year, then you have to validate these models for like 6 data points. It becomes extremely difficult. So certainly developing better benchmarks that are deeply rooted in physics and math to understand where these models might fail, I think that would be essential. I think that's a great area for mathematicians and science talk. So I really think that's a great area to focus.
Okay, thank you, Pedram. One more. We have one question in the chat. I don't know if you see it, Pedram, but I can read it if you prefer.
I can see it. Can we learn physics from more data, maybe as you mentioned, using other regional information at high spatial resolution? Yeah, I think it depends on the more data and where that data comes from. I mean, here we found that even if we remove 25% of the era 5 data, we get the same accuracy. I think others have even done experiments with removing half of the data and you get the same level of accuracy. But I totally agree that if there is more data, but maybe that if they're strategically sampled from where there was an extreme event or something different from what the model has seen, then they could be very useful. But again, the question is where to sample, and that's where this idea of rare event sampling would come from. But certainly knowing more about the physics of the system, we can think where maybe to do more simulations, high resolution simulations, and bring more data into the training set. I think those are areas to explore. I totally agree.
Okay, thank you. Any other questions? Don't be afraid, and now is the time for the good question.
Yeah.
Any questions? So if there's no more question, is pretty much
I'll
last call.
I'll ask you a quick
Okay,
question.
go ahead.
So you talk. I mean, you talked a few times about the cost of running these large simulations on big machines for conventional models, but how do you balance out the training cost as against the simulation cost overall? Because there are, those costs are sometimes hidden. And sure, you've got a very fast evaluation process, but you've got a huge amount of training, which is what's it going to do? Consume more electricity than Japan in a short space of time? So how do you balance those two things out, do you think?
No, that's a great question. As much as we keep saying these models are super fast and it's like a fraction of a second, training these models actually is very non-trivial. And it takes several days and several A100s to train ForecastNet. And the models like GraphCast, Pango are much more expensive. And I think people have done that kind of analysis. I haven't done it myself, but still the cost of training the model overall, because it's something you need to do only once, right? But of course there is, development stage and validation, HPO. Still, I think it would be much lower than the cost of doing multi-ensemble and large ensemble forecasting each time for an extreme event, right? Because again, for a lot of these events, we need probabilistic forecasting, right? And the AI model, once trained, doing probabilistic forecasting is very, very trivial. So overall, I think the training costs for these models, which are still much cheaper than things like LLMs, it still is not much compared to what we gain from the inference of doing probabilistic forecasting. But again, I agree. I think that's something that's becoming a concern about, well, just the cost of developing these models. And now, like all the ideas about foundation models that are going to be much bigger because they're going to ingest all kinds of different data, climate data, heterogeneous data. So yeah, I think that's something to think about. But it's much cheaper than NWP and GCMs.
Thank you. Gian Giacomo, you have a question or comment?
I can unmute myself. I have a question. So do you say about the part you mentioned of adding the physics into the AI model? Do you think equation discovery can be a useful approach for this part? Because I'm more in biochemistry. In biochemistry, we lack a set of dynamical equation, which is a very great source of uncertainty. So I was wondering if this is an area of a research you have investigated.
I agree. I think in many fields that are newer and we even don't have, good representative, like mathematical model, I think equation discovery can provide a good starting point. For things like closure modeling, when a lot of work has been done in the past few decades, for example, we have a paper that we did equation discovery on that pi term, the subgrid scale term, and we found something that turned out to be something known from the 70s that you could get from Taylor expansion. So of course, if we didn't know that, then this was something very useful. But again, something like closure modeling for turbulence has been studied a lot. But for like the area like the VGC that you mentioned, maybe land feedback to the atmosphere, things like that, I think equation discovery can be a great starting point that can guide mathematicians and physicists. For the problem here, I'm not sure exactly what is the physics, and I think that's something we are thinking about, and it would be good to chat about that more. But it's exactly like what physics need to be added to the model without hurting predicting other stuff, right?
Right.
I think
Right.
that's the problem. Yeah.
Thank you. That was a very good answer.
Sure. Thanks.
Okay, thank you. Any other questions? Okay, so if there's no more questions, pretty much last call this time. Thank you very much, Pedram, again. Thank you also much for organizing and helping us. And yes, I wish you all the best for the rest of your day if you still have some hours in it. And if not, remember we have these meetings once per month, and we also have other community meetings where everybody goes into breakout rooms, and then you can ask questions about careers, etc., or other things that you may be interested in, new research fields, new ideas. So there should most likely be another one. So make sure to, if you're not a member of SIAM, and if you want to get these emails, make sure to become one. If you're a student, it's for free. So, no excuse of not being one. Okay, thank you very much and all the best. Thank you again, Pedram.
Thank you. Thanks for the great question.
Thanks very much, Pedram. It was
Thank
very
you.
great. Thanks.